Hi, this is a U substitution lesson for Calculus AB, and you have your notes in front of you, I hope, but that's really all you're going to need are your notes and a pencil. And you can see at the top of the notes I've written you, just as the power rule for integrals is true when we just have an x, right? We go up an exponent, divide by that new exponent, and add a constant. This statement is also true. The only difference between these two statements is u versus x. And understand that we mean here that u is a function of x. It's really important to notice that in order for this statement to be true, we need to have the derivative of u next to the thing that has the exponent. And so you will see in the problems that we have today that that's mainly what we're looking for. We try to get things to have this format. Important to recognize what u is and to have the full derivative of u, and if not, we might have to do some adjustment. And then once we have that form that I just circled in blue, then we can apply the rule. And that's really all it comes down to. So because this is a big time how-to lesson, I thought it was a good one to do by video. Okay, when we look at this integral, we might not have an idea of how to do it initially because we certainly can't do algebra like distributing this into the radical. That is not true. We might say, well, I could take the square root of each part of the radical. That is also algebraically untrue. So the only thing we can do is try to see if this integral fits the format of something else that we know. And what we can try here is doing a little substitution. So my intuition and my experience are telling me that the glob in this problem is the part that's underneath the radical sign. If that is u, the derivative of u with respect to x would be 2x. And then we can move that 2x, or the dx, to the other side essentially, and have this. Okay, now that looks great because 2x dx, haha, that's right here. Okay, and so if we were to rewrite this problem in terms of u's, we have the thing we called u inside our square root sign, so that's u to the 1/2, and the pieces underlined in blue are the derivative of u. Now that integral we certainly should have control over. Okay, we can just apply our power rule from up above. Okay, and say, well, that's u to the 3/2, and I divide by 3/2, so that's multiplying by 2/3, and add a constant. And I need to be cognizant of the fact that that can't be my final answer because the question didn't have a u in it. I was the one who put the u in it. So I have to go back into x's. So this u, it says over here, is this. And this is a square root. And then I need a cube on that, so that's to the 3/2 power overall, plus a c, okay? And that would be my final answer. Now there might be a few of you, maybe even a lot of you, who can look at this original problem, and you can see what has to happen without making this formal u substitution. That is more than fine. This is just a technique to help you get unstuck and help you see pattern if you aren't seeing pattern, okay? There are times that u substitution is handy. There are times that u substitution is not handy. This is one where I could do this problem another way. I could use algebra first. I could do some FOIL over here and then distribute in this term. I'd have a nice long polynomial, and certainly we know how to find antiderivatives for polynomials. But rather than do that, I feel like there's a relationship between the two things that I see in the problem, the two quantities that are in parentheses. So how about we try this? Okay, if u is equal to that second parentheses, that quantity in the second parentheses, du is going to be 3x squared plus 6, then move the dx over. Okay, now look how nicely that lines up. It's like someone wrote the problem just to exemplify this. That part here that I underlined is du. And then this piece is u squared. So I have this nice simple antiderivative to find, 1/3 u to the 3rd, plus a constant. The constant should arrive on the scene as soon as you antidifferentiate. And I've got 1/3, now sub back in, x cubed plus 6x, quantity to the 3rd, plus c. Easy peasy. Okay, problem 3 says sometimes you need to make a small adjustment if the du isn't present. So you'll see here that we find a very clear substitution. I mean, it should be somewhat obvious as you look at this that this part is the glob or the u. Seems like that would be the case, our intuition tells us. But when we take the derivative, we get 12x cubed dx. And I look back to my question now, and I say, well, I've got the x cubed and the dx, but not so much the 12, right? This is what I do. And there are, if you go to the MRC, by the way, different teachers kind of show this part differently, but I show it like this. I say I needed a 12 on the inside, so I needed to balance that with a 1/12 on the outside. I'm really multiplying. If you look at the part that's written in red, I'm really multiplying by the number 1. 1/12 times 12 is 1, and that's what keeps it legit, right? Mathematically legal, is that I'm just multiplying by 1. Now if we switch over to u's, the part underlined in green is u to the second, and all these pieces in red here were those. So that's du. Okay, now I'm ready to do my nice anti-differentiating. So I've got 1/12 hanging out in front, that's just a multiplier, and then I have 1/3 u to the third and a constant. And then we will substitute back in. So we've got 3x to the fourth plus 1 is u, that's cubed, over 36 plus c. So sometimes you need to do a little adjustment of a multiplier, okay? Question 4 is an example where u substitution just won't work, okay? You think, looking at this perhaps, oh, this looks like something where I could use u substitution, and I'll take that blob and I'll differentiate, and I've got a 2 and a dx, but there's this variable part. Like I could adjust for the missing 6, right? 2 to make that 12, I could multiply by 6 and 1/6, but that's not going to be enough. And you can't actually insert variables. That does change things, okay? So this is a case where u substitution just isn't the strategy. We're going to have to use something else, like let's say algebra. Pull out the 2, which is legal to do, and then FOIL this out, okay? And you would have 9x to the 8th plus 6x to the 4th plus 1. Can you hear me thinking there? I had to do a little arithmetic in my head. Whew, brutal. Okay. And then anti-differentiate. So the 2 is out in front, and then all these anti-derivatives. So we'd have x to the 9th divided by 9. That's going to cancel that 9. X to the 5th divided by 5. That doesn't cancel the 6. And this is an x plus a constant. Okay? And so you can tidy that up as much as you feel like, which maybe is not at all, but you could write this, okay? But that is a time when u substitution doesn't work. I mention this because every year I have taught calculus, I find some people who fall in love with u substitution. It doesn't fix everything. It fixes a lot, but not everything. Okay, here's an example where you're going to have what I would call a little bit extra, okay? It's sort of like problem 3 where we had to do a bit of adjustment. You'll see. Let's let u equal that glob that's inside the radical. The derivative would be this, okay? And so now we compare with what we have. This part is going to be u to the 1/2. But look at this. We've got 5x dx. We want 2x dx. So the way that I would think about this is to say, well, let's take that 5 and pull it out in front. And then I really would like to have a 2, but I need to balance that with a 1/2. So I would say that this is the same as 5/2 times the integral. Now the 2 dx and x, 2 dx and x are all making du. Okay, so those parts all together, and then the part that is u to the 1/2 is this part right in here. Okay, so that's kind of messy looking to me as I stare at it right now, but I hope you understand. If not, rewind, try again, see if you follow, or ask me tomorrow. Antiderivative here, we're going to take u to the 3/2, divide by 3/2, add a constant, and then we have a little bit of cleaning up we could do and a replacement. So 5/3 u is x squared plus 1. You can write that with a radical or with that exponent. And there you go. Okay, we've got one more. Okay, whoops, we don't have one more. I thought we had one more. I think I lost a page. Shoot, that's not even what I wanted. Okay, but here's number 6. Here we go. Okay, so that guy. All right, let's let u equal 1 minus 2x. du would equal negative 2 dx, okay? Now, if you check it out, we don't have a negative 2. And so I have shown you already the idea of inserting a negative 2 and a negative 1/2, and you certainly can do that method here. But I just thought I'd show you an alternative, because as I mentioned, some other teachers do this a little differently. This is the other way. You could also solve for dx. This is equivalent. Okay, so all I did was I divided both sides by negative 2 over here. Okay, and so with this and this, you can just replace stuff. Okay, so go back to the problem now. Say, well, this is the same as the integral. This part is u, so that's u to the 1/2. And dx is the same as this, negative 1/2 du. And then pull out the negative 1/2. Now that is exactly the same as what you'd get with the little tweak that I typically do, putting something inside and putting something to balance it outside. But whatever, I'm just showing you, okay? Take it up to the 3/2, divide by 3/2, add a constant, and then replace. So this would be negative 1/3 square root of 1 minus 2x to the 3rd, quantity to the 3rd, plus a constant. That's it, okay? So that's basically all I need to talk to you about now. There are some things that happen with definite integrals. We will talk about that while you're working in class. Please make sure that tomorrow you come to class with your, actually there's a little bit more. Hold on a second. Okay, never mind. I was holding a big mass of papers and I wanted to make sure I'd covered all the examples that I gave you. So tomorrow, make sure you come to class with your textbook and your homework notebook, and we will just work and make sure that I also clarify for you what happens when you have a definite integral and use substitution, because there is a little bit of a twist to it, but it takes 2 minutes to explain, so no big deal. But this is enough for tonight, and I will see you tomorrow. Thanks a lot. Bring your notes to class too. Okay, bye-bye.